So how many of you know the fast way to find Taylor series? Of like a multivariable function? Or let's say I give you the sine of 1 minus xy, and I want to find the Taylor series. So I've got to take partials with respect to x, partials with respect to y, partial, and 2 partials, 3 partials, all those mixed partials. Right? Does anybody want to calculate the multivariable Taylor series expansion of this? No. I do. Do you accept the volunteer? You've been volunteered. Okay. What's the sine of 1 minus u? What's its Taylor series? This should be equivalent to asking you, what's your mother's name? What's your father's name? This should be that good of a friend. Well, actually, based on personal information you've told me, I can probably figure it out.
Oh, yeah.
Well, I don't want to say anything in public, but right?
1 minus u.
Not 1.
The quantity. Oh.
It's. Oh, I'm sorry. Oh, sorry. I gave you 1 minus u. Oh, sorry. Right. So that would be 1 minus u plus 1 minus u. I'm sorry. Minus 1 minus u cubed over 3 factorial. So you can just do it like that. So if I give you the sine of 1 minus xy, this would be 1 minus xy minus 1 minus xy cubed over 3 factorial. Now, if x and y are close to 1, this isn't going to be that bad, but it's still going to be painful. If instead I give you the sine of x squared plus xy, then that would just become x squared plus xy minus x squared plus xy cubed over 3 factorial. And this is going to be really nice. Every term here is of degree 2. Every term here is going to be of degree 6. There's no mixing and matching. So when I expand this, I know there's no constant term, there's no linear term, this is the quadratic term, there's no cubic, there's no quartic, there's no quintic. Here's this. If I gave you the sine of x plus xy, that's a bit more painful. That's going to be x plus xy minus x plus xy cubed over 3 factorial plus. And now I've got to be a little bit careful. I could have things mixing and matching. So this will be the linear term, the quadratic term, the cubic term will be here. The quartic term will still just come from here. The quintic term will come from things from here and things from the next one. So for a lot of functions, you can actually do Taylor expansions fairly quickly if you remember Taylor series expansions in one variable and then substitute things in. It's just a good trick to have in your arsenal. Okay, so you were all given a challenge problem. Can you come up with a sequence of points that that go off to infinity, such that my product is well defined? So I want sequence an. The absolute value of an tends to infinity, and I want the product z minus an to be well defined. I want this to converge at least somewhere. This is not going to be possible. Right? Unfortunately, when I try to understand this, well, if I fix z inside a giant circle of radius r, the ANs are eventually going to just dwarf this in terms of size, and this is going to go off to infinity. So, won't converge. Alright? Very sad. But maybe there's a way we can tweak the problem. So why was I writing it as z minus an? I wanted something that will be 0 when z equals an. Can you give me another way of writing a factor that has a 0 when z equals an? So I want something that's 0 when z equals an. Z minus an is bad because as an goes to infinity, if zn is fixed, this is going to just diverge.
Z minus an over an.
So I could try z minus an over an. And that would give me, I'm just going to rewrite it a little bit. 1 minus z over an. This is essentially what you have. I'm just flipping a minus sign. If I write it like that, things are much better. And now I actually have something that has a chance of converging. Why? Well, if an is getting really, really large and z is fixed, these factors look very close to 1. If I multiply a lot of things that are close to 1, what do I expect to get? Something hopefully close to 1. And so the goal here is to just make sure that this will converge. Now the problem is it's not always going to converge. And sometimes it may converge to 0. And so the question is, given a sequence, will I be able to make sense of this? So the book just immediately jumps to this. It skips this step. And I want to go through this to give you some idea of why we started looking at factors like this. This is the most natural way to try to build up a function that has zeros at the prescribed places and nowhere else. But I need to understand, does this product exist? So this leads us to studying products. And now, as soon as I wrote that, some of you are already thinking logs, right? So again, whenever you see the word product, Pavlovian response, you want logs. Okay? So now the question is, how can we understand products? So consider a sequence an, and I want conditions so that the product n goes from 1 to infinity of 1 minus, or let's say 1 plus an, converges to something non-zero. I assume somebody can give me a condition where this will converge to 0. Yeah, if an is -1. If any of the an's is -1, the product will converge to 0. Okay, so let's stay away from something like that. That's not too interesting. So what we want to understand, when does this converge? So let's imagine we have a sequence of an's. What can you tell me about the magnitude of the an's that this is going to have a chance of converging? So the magnitude of the an's are not going to 0. Well then, if I have a factor whose absolute value is, say, at least 1 plus epsilon, then this is going to go off to infinity, right? So if the magnitudes of the an's do not go to 0, we're dead. Right? There's no chance of getting convergence. Yes?
You have 1 plus an, so if an is greater than 0, this is always going to diverge, right?
Well, let's try something. Let's say 1/2. Let's try to do this right. 2/3, 3/4. Okay, we'll do it the other way. Sorry, you want it the other way. 2/1 times 3/2 times 4/3. Okay, this will blow up. Let's take a second to just figure out. I think this is what I want. It goes from 1 to infinity of n squared over n squared minus 1. So this is the same as the product, and it goes from 1 to infinity of n times n over n minus 1, n plus 1. So if I start writing this out, you agree that each of these factors is greater than 1. This is just the product, and it goes from 1 to infinity. N squared I read is n squared minus 1 plus 1. So it's 1 plus 1 over n squared minus 1. So each factor is greater than 1. Over here, I'm going to get, alright, should I really start the product at n equals 1? No. We'll start the product at n equals 2. So we'll have 2 times 2 over 1 times 3. Then the next one will be 3 times 3 over 2 times 4. Then 4 times 4 over 3 times 5. Then we'll do 2 more. 5 times 5 over 4 times 6. 6 times 6 over 5 times 7. And let's look at what the product equals. These 2's cancel, these 3's cancel, these 3's cancel, these 4's cancel, these 4's cancel, these 5's cancel, these 5's cancel, these 6's cancel. And as I march down the line, this number is going to get closer and closer and closer to 1, and then multiplied by 2. So what does this product converge to? It converges to 2. So it's possible to have an infinite product of terms greater than 1 and have it converge to something finite. What is going on here? what's going on here is a lack of uniformity. Okay? Lack of uniformity. How many of you have seen contraction maps?
The what?
Contraction maps with fixed point theorems?
Not really.
Okay. If you had it, would have been a great example, would have completely illustrated everything. You would have been, oh, of course. All right. The difficulty here is while all these numbers are greater than 1, they're not all greater than 1 by the same amount. There's no fixed threshold such that every number is at least epsilon above 1. And that's the difficulty. As I go further and further down, they're getting closer and closer to 1. If there was some critical cutoff, here's 1 plus epsilon. And if everything was up into here, then the product would blow up. Because every factor would be at least 1 plus epsilon. What's happening is, if they go down to 1 sufficiently rapidly, it will converge. What do you think will happen if it doesn't go down to 1 rapidly? It'll blow up. So in fact, the example I was originally giving, 2 over 1 times 3 over 2 times 4 over 3 times 5 over 4 times 6 over 5 times 7 over 6, dot, 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 dot. Each factor is getting closer and closer to 1. Now when I cancel, however, I see it goes off to infinity. And so here, I'm not converging fast enough. If you think about what's going on, how fast am I converging to 1 over here? Roughly at what speed? Around 1 over n squared. Over here, how am I converging to 1? 1 over n. This is the product of 1 plus 1 over n. So this is great. So again, I've been having some conversations with colleagues about how should one teach. Should you have a completely rigid description of the day's lecture, or should you be more fluid and organic and just see what happens? So you've independently given me what I wanted. So I appreciate this. Right? Here, I have something like, my an is like 1 over n squared. So here, an is like 1 over n squared. Here, an is like 1 over n. What's the difference between these? What's the difference between these two? One diverges, one converges. Right? Here, the sum of an squared converges. Here, the sum of an diverges. So, sum converges, sum diverges. Ah! What happens with this product? Converges. What happens with this product? This product. Diverges. So what conjecture would you make? So when will a product of 1 plus an converge? If the sum of an converges. Have I asked you to simplify that in this class yet? No? Okay. Can somebody tell me in lowest terms what 16 over 64 is? 1/4. 19 over 95.
You can get rid of it.
Very good. Right? 49 over 98.
Get rid of the 9. This is based on a Project Oil question, right?
There's something along this for one of the project orders.
Yeah, because I remember.
So as was suggested, cancel the 6's and you get 1/4. Cancel the 9's, get 1/5. Cancel the 9's, get 4/8, which is 1/2. So therefore 12 over 24 should be 1/4. Just because you check something once or twice does not mean it's a proof. Right? So just because we've checked the sum of a over n converges implies the product converges, diverges implies the product diverges for that one case does not mean we've even remotely proved the result. But we at least now have some intuition. And if you haven't seen Project Euler, there's a lot of fun stuff there. There is a Project Euler problem related to something like this, with strange ways of doing divisions. So our conjecture is if the sum of the a, let's put in absolute values, converges, then the product 1 plus an converges. And what it means for the product to converge is just take finitely many terms in the product, evaluate it, and then take the limit as your cut goes to infinity. Alright, so let's prove the conjecture. So if the sum of an converges, then what do you know about the absolute values of the ans? I'm sorry?
They go to 0.
They have to go to 0. If they don't go to 0, there's no way the product can converge. There's no way the sum can converge. So because the sum converges, the individual terms have to be tending to 0 in absolute value. If they tend to 0 in absolute value, does the sum have to converge? No. You know, the harmonic series 1 over n is the most famous example where it doesn't converge, even though the terms tend to 0. But we know the ans tend to 0. So the book in this chapter uses the following technique many, many times. For n big, the absolute value of an is at most a half. In fact, you can make it at most whatever you want, you know, that's greater than 0. Because it converges to 0, you give me any epsilon, and then from some point onward, the individual terms have to be at most epsilon. And so all we really need is a number that is less than 1. And so, you know, 1/2 works well for this. Why would we want something like 1/2? Well, now, if you look at 1 plus an, if you try to think, where could this live? So here's 0. Here's the negative reals, which we're going to throw away. Here's 1. And now I have a circle about this of radius 1/2. And so, if n is big, then an has to live inside here. What this means is the log of 1 plus an is defined. Right? I want to use logarithms, I've got to make sure the logarithm is defined. If an was too large, I could be going all over the complex plane. I need to be able to cut off a slit in the complex plane. That's why I need anything less than 1. Okay? So now the logarithm is defined, and we actually know, and this is why I was happy to talk about Taylor series at the start of class today, the log of 1 plus u is u minus u squared over 2 plus u cubed over 3 minus u to the 4th over 4. The pattern is hopefully clear. Okay? So we have a formula for the logarithm. Now, if the absolute value of an converges, what about an squared? Converges. Why?
It has to be going to 0 faster.
Has to be going to 0 faster, right? Because my ans are going to be less than 1/2 from some point onward, when I square them, they're even smaller. So if it converges before, it still converges. Okay? So we know that the sum of an squared will converge. An cubed, it will converge. And in fact, what's nice is they'll all converge to something at most the previous. We can almost see like a geometric series formula coming in here to help us with the estimation. We have a little bit of decay from alternating signs and from the stuff down here below. We're not going to really need it, but it's just good to have a sense of what we have. Okay? Just trying to give you, a feel for what we have and why we're arguing the way we are. When I expand this out, this is going to be the main term. If an is getting closer and closer to 0, then an squared is going to be significantly closer to 0. Okay? So we have, the Taylor series expansion like this. So now, let's consider that the product, n goes from 1 to infinity, n of 1 plus an. So there's a little bit of bookkeeping that we need to do here. Is it true that the logarithm of 1 plus an will be defined for all values of n?
No.
No. Technically what I have to do is break this up into a product. N goes from 1 to m minus 1, 1 plus an, and then a product, n goes from m to n of 1 plus an. Because here, the absolute value of an might be greater than 1/2, but in here, the absolute value of an will always be at most a half. And there can only be finitely many bad terms because it converges. So only finitely many. Okay? What's the easiest value to assume for m? What would be nice? 2. A little lower. 1. Right? It would be nice if every term was just less than or equal to a half an absolute value. Right? We can always assume that. Just throw away the finitely many terms that are greater than 1/2 an absolute value, and then just put that in at the end of the day. So if you want an argument like this, you can almost just say, screw it. Let's just assume that m is equal to 1, and that all the terms are less than a half an absolute value. Okay? It's really not that much work to write the big letter m rather than the big number 1 down below, so I will try to do the more general case. So we study the log of the product, and it goes from m to n of 1 plus an.
Now, why are we using the big N here and not just going off to infinity?
Well, then we'll let big N go to infinity. So we're truncating the product, and then we're going to try to understand what this is.
That'll do.
Okay. So there's lots of different ways of doing this. And so one way to do it, the book does it by using exponentials and writes, 1 plus an as the exponential of the log of 1 plus an. And then when we have the product here, we'll have sums over there. The difficulty is we want to be able to say the log of a product is the sum of the logs. Another thing we could do is, the only difficulty is whether or not this converges to 0, or does it blow up to infinity. So if I want to understand how big this is, what could I assume about the ANs? What's the worst possible case?
They're all equal to 1/2.
No, that can't be the worst possible case because it converges. So if this product is going to be as large as possible, if I give you an AN of a given magnitude, what would be the worst possibility for me for its direction? So what would make this the largest possible?
The n are positive.
They're all positive. And what would be the worst possibility? They're negative. So what we would get is the product, n goes from m to n of 1 minus an in absolute value, is less than or equal to the product, n goes from m to n of 1 plus an in absolute value, is less than or equal to the product, n goes from m to n of 1 plus the absolute value of an. So if I want to try to understand the behavior, I can sandwich it above and below and understand these different things. And I can then get my convergence arguments. So there's lots of different ways you can do the algebra. For me, I always find it nice to look at best case, worst case scenarios and just understand what's going on in the best case, what's going on in the worst case, and then figuring things out. The other advantage of this is, what kind of numbers are 1 plus absolute value of an? Positive. Right? They're real numbers. And I can use standard stuff about logarithms. Right? So I don't have to be working with a complex logarithm if I do this.
We know it's all going to be positive?
No, because the ANs are complex numbers in general.
Oh, okay.
Right? So I don't necessarily know anything about the... I don't know that the ANs are real valued.
No, I'm just saying that the products are all going to be positive because we're doing n to n, so we've assumed already that an is less than...
No, well, less than half an absolute value.
Sure. But we're working with absolute here, so it's always going to be products and positive.
Wait, but I'm saying, if I look at this over here, yes, an is less than a half an absolute value, but maybe it's I over 10. And now I have 1 plus I over 10. And so if I want to take the log of 1 plus I over 10, if I want to take the log of a product, I would now need to know the log of a product is the sum of the logs. I would need to do that. And again, that's worth proving.
We don't know that yet.
We haven't proved that. Right? That was an extra credit problem for you to think about. We haven't proved it. By doing this trick over here, I've passed back to a real case. And then if I can show that when m is really large, that these two things are really close to each other, then by the sandwich theorem it's going to have to converge. So I'm basically doing a detour and going back to real variables to avoid having to work with finer properties of the logarithm and just convert. So we can now assume without loss of generality that all of our a's are positive, just so I don't have to keep writing absolute values. We'll do the case of the upper bounds, the lower bound is handled similarly. So without loss of generality, assume ANs are greater than equal to, are greater than equal to 0, and the, I guess, the absolute value of AN, so AN is less than equal to 1. If we can handle this case, we can handle everything by the sandwich theorem. So now we have the log of the product of 1 plus AN, and it goes from m to n. And now that's the sum, and it goes from m to n, of the log of 1 plus AN. Okay. And so now we want to figure out what can we say about that sum. So now, what do we have? So we have the sum, and it goes from m to n. We'll now have AN minus AN squared over 2 plus AN cubed over 3 minus AN to the 4th over 4, yada, yada, yada. This is where life is just barely annoying. I would love to say the sum of the, I would love to basically just split the sum and do each term term by term. The sum of AN, the sum of AN squared, the sum of AN cubed. The problem is I don't know what's the sum of AN squared relative to the sum of AN. It's smaller, but by how much? Right? The problem is if I try to just break it up in terms of individual pieces, maybe the sum of AN is 5. Maybe this is 4, this is 3, you know, I could have all these difficulties. And I'm squaring things and cubing things, and I have alternating signs. Right? So there's several different ways to approach this. One way to approach this is say, you know, screw this, you know, drop off all the stuff over here, and that's an upper bound. I only need an upper bound. And so if I drop all the terms, one approach is the log of the product, and goes from m to n of 1 plus AN, is less than equal to the sum, and it goes from m to n of AN. And that converges. That's the simplest thing we can do. And in fact, if m and n are very large, we can make this arbitrarily small, so we'll get that the differences between these two are sandwiched.
Well, it's not going to converge once again goes to infinity, right?
It is, because we assume the original series converges.
Oh,
Right. This is the simplest way I know to finish the analysis. If you want, I can show you the most complicated way to finish the analysis.
Yeah, let's do it.
Let's do it. Alright, so we need to roll up our sleeves and we need to do a really complicated stuff, and this will make you appreciate the elegance of the simple argument.
I regret this decision.
I'm sorry? Did you say you already regret the decision?
Go to graphic development.
Well, I mean, it's worth seeing. So look, there's a lot of bad decisions that are made in life. You know, next Friday, for instance, we may be thinking about a very bad decision that was recently made. No. Since this is being recorded, I don't want to say what potentially bad decision was made either last night or this morning. Okay? Alternate. So we have the sum of AN minus 1/2 the sum of AN squared plus 1/3 the sum of AN cubed plus dot 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 dot. I'm sorry. Okay? So here's one way to try to handle this. This is clearly less than equal to the sum of AN plus 1/2 the sum of an squared plus 1/3 the sum of an cubed plus dot, 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 dot. And in fact, I don't even need the decays from the 1/2, 1/3, etc. I can say this is just less equal to the sum of an plus the sum of an squared plus the sum of an cubed plus dot, 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 dot. Do you know anything about the sum of an squared relative to the sum of an? It's smaller. Good. Can you quantify smaller? Yes, you can.
It's at most half.
It's at most half. Each an is at most 1/2. Excellent. Make sure you email me. Each an is at most 1/2. So this sum is at most 1/2 times the sum. So let's equal to the sum of an plus 1/2 the sum of an. What about the sum of an cubed? It's at most 1/4 or 1/2 squared sum of an plus 1/2 cubed sum of an. Look, now I have a geometric series. 1 plus 1/2 plus 1/2 squared plus 1/2 cubed. That sums to
2
2.
1/2. Okay, 1, 2, yes. Yes.
I think you hit every number between 0 and 1. What was it?
2.
2. 2 sum of an. And so rather than just getting the sum of an, we get twice the sum of an. And again, I could have done a little bit better by having an alternating sum here maybe. But if I have an alternating sum, I've got to be careful. Am I over-subtracting or under-subtracting? You've got to be very careful. Fortunately, because I know the an's are at most 1/2, I can do something like this. So if you weren't clever enough to see, I just need an upper bound, drop it over here. Then a longer argument like this will still work and give you a good answer. So it's not hard, it's not that bad. Okay? So what we've been able to show is that if the sum of the, yes?
Never mind that question.
Okay. So, you should have said, really good question, but I solved it. That would have been much better. So what we've been able to show is that if the sum of an converges in absolute value, then the product converges. So now we have a condition for convergence. Okay, so now, any questions on this argument before we now return to our problem? So we want to build a function that will always vanish at the prescribed places, but no place else. And this is going to be extremely useful in terms of understanding certain functions. I want to be able to express functions in terms of their zeros. So what we're going to do is look at what's called Weierstrass factors. And I think the book uses a capital E for the notation instead of a WES. So E0 of z is 1 minus z. En of z is 1 minus z e to the, just want to make sure there's two notations. Then we'll do it with a pause. Okay. Z plus z squared over 2 plus z cubed over 3. Okay, they're doing this. Okay. Plus dot 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 plus z to the n over n. Okay. So the question, first of all, is why would we define it this way? Yes?
I have a question on the stuff we were just doing.
Okay.
So we proved if the sum converges, the product converges?
Correct.
Is it if and only if?
So I'm going to let you think about that.
All right.
So, excellent question. Can the product converge without the sum converging? And so, when you have something like this is exactly what you should be doing. You should be thinking, well, what if I try to flip it around? Can I come up with some kind of pathological sequence where maybe I have products canceling with each other in very nice ways, but I could have some issues with the sum? There's also a lot of, well, what goes on if my sum is only conditionally convergent, but not absolutely convergent? If there's a lot of cancellation in terms, then all of a sudden things become very difficult. So here, I'm being very nice to myself. I'm giving myself absolute convergence. So when you see something like this, the question is, why is the book defining something like this? Does anything here look familiar to you? Yeah, this is like a truncation of the log. Right? if I start expanding, the log of 1 minus z is negative z plus z squared over 2 plus z to the n over n. So what I've done is I've truncated the logarithm. And so, if I take 1 minus z, if I write 1 minus z as e to the log of 1 minus z, notice something. There's going to be a huge amount of cancellation. And so the whole point is this should be very close to what number? This whole product. E n of z should be close to what number? 1. Because this is looking like e to the log of 1 minus z. When I expand, this would be e to the negative z plus z squared over 2 plus z cubed over 3. And here I have a plus sign. So when I multiply them together, I add the exponents. And the first n terms cancel. And I'll have a sum of z to the n over n plus 1 plus z to the n plus 2 over n plus 2, dot, 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 dot. So their product should be very close to 1. So the question is, can we quantify how close to 1 it is as a function of n? And so the way you should think about these is we're basically adding convergence factors. Now, these convergence factors, our goal, it's always nice when you have a long lecture to try to remember what is the point of this, what are we trying to do? We're trying to find a function that has zeros at the prescribed places and no place else. And we saw there was a lot of trouble trying to build that up. Craig gave a nice candidate. Unfortunately, it was identically 0 inside the disk. It blew up outside the disk, and strange things were going on the boundary of the disk. If I give you a sequence, how can I build things? We saw that there was problems with convergence when I just looked at the product of 1 minus z over an. Does this add any zeros to my function? Where's this function 0? At 1. And so instead of looking at log of 1 minus z, what do you think we'll be looking at in a little bit? I'm sorry?
1 minus an.
Almost.
A minus c.
Nope.
1 plus an.
Nope. It should involve z and an.
Of z over a.
Yeah, 1 minus z over an. So the goal would be to look at things like en of z over an, and maybe take a product over all of these. And that's going to have zeros where we want it to have zeros, but it's going to give us these exponential factors, which will hopefully give us convergence. So the idea is you fix things locally. Okay? You locally fix things so that when you combine them all at the end of the day, the product will make sense. Yes?
I just have a question.
Yep.
So you say that 1 minus z is about equal to e to the log of 1 minus z, but then, didn't we... Never mind.
Okay.
That's all.
Another good question. So much easier teaching at Williams than other schools.
Well, I guess I'm wondering then, so were we saying that e n of z is what's going to 1?
Yes.
And why is it going to 1?
Well, because if n is very large, 1 minus z times this. If you look at this, here's the log. Here's 1 minus z. It's e to the log of 1 minus z. It's e to the negative z minus z squared over 2 minus z cubed over 3.
Right.
When I multiply it by this fact of e to the z plus z squared, the z and the negative z cancel. The z squared over 2 and the z squared over 2 cancel.
Oh, you mean when you multiply
Well, that's what en of z is.
1 minus... Oh, I see.
So en of z is going to look like e to the negative z plus z squared over 2 plus dot 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 times e to the z plus z squared over 2. But here, I stop at z to the n over n. And so now, when the dust settles, I have e to the negative sum k goes from n plus 1 to infinity of z to the k over k. And the question is, how large can that sum be?
Can't we write that as a infinite product and use our previous things?
Yes. I would say here, I would rather keep it like this rather than convert it to an infinite product. But I mean, in some sense, we do have an infinite product as written.
If z is outside the unit, that's what we have.
So what kind of value do we want to assume about z?
Real.
So if you have a sum of z to the k over k, you should be thinking something, what z's do you like?
Less than k.
Well, k is my index of summation.
Less than
Less than 1. If it's less than 1, it's going to be dominated by geometric series. So, in fact, we'll take if z is less than or equal to a half. That's the critical threshold we're going to be using. And you should think later that when we have something like this, z is eventually going to be z over an. And we're going to be applying it in that case. If z is less than or equal to half, then the sum, k goes from n plus 1 to infinity, of z to the k over k in absolute value. You want to know how big could this be? How small could this be? What's the danger for us? Do we want it to be big or small?
Small.
Well, the smaller this is, then the closer this is to 1. The bigger it is, the closer this is to 0. So the danger is actually when that sum gets too big. So we want to estimate how big can it be, how small can it be. So this is clearly going to be greater than or equal to, we want to make sure it doesn't get too big. So it's less than or equal to the sum, k goes from n plus 1 to infinity, of absolute value of z to the k. Right? I'm dropping the fractions, and I'm putting the absolute values inside. This is the worst possible case for me. And in this worst possible case, this is going to be z to the n plus 1 over 1 minus absolute value of z. Well, what do I know about 1 minus absolute value of z? It's greater than a half. So this should be less than or equal to 2 times z to the n plus 1. So this fact is going to be very close to 1 if z is less than a half and n is large. So if absolute value of z is less than or equal to half and n is big, then E and z is very close to 1. And we can quantify how close. No. It's at least e to the negative 2 z to the n plus 1. And so if you look at the expansion of that, that's 1 minus 2 z to the n plus 1 plus 4z to the 2n plus 2 over 2 factorial plus dot 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 dot. But if z is less than 1/2 and n is large, this term really doesn't matter relative to this. So you can see how much I'm differing from 1 by. Okay? Any questions on what we have here? So we've just shown that E and Z is very close to 1, and we can even quantify how close it is to 1. Now again, in order to get the savings, I need n to be large and I need z to be less than half. The larger I make n, the closer it is to 1. This should be found under the no duh category. Right? Why does it make sense that the larger n is, the closer it is to 1? Well, the difficulty is I have a infinite series for the logarithm, and I'm approximating it with a finite series. The longer my finite series is, the better the approximation should be. So it's reasonable that the larger n is, the better the approximation. So now this gives us a way to try to build our function. Right? So now that we're going to use these ENs, we're going to build a function that has the prescribed zeros. It's not going to be the most efficient way to build the infinite product, but it will be a way that works. If you know more information about the function, you can do something better. So, building a function vanishing only at the ANs, with the ANs going to infinity. Okay? So what we'll do is we'll let f of z, let's just try this. The product n goes from 1 to infinity. So give me a factor that vanishes at
Yeah.
0 a.m. So let's just try something like this. So just writing this out in Explorer, n goes from 1 to infinity, 1 minus z over an times e to the z over an plus over dot plus 1 over n z over an to the n. So notice that what I'm doing is I'm using the Weierstrass factors, and for each 0, I take the next largest Weierstrass factor. There's one thing I've done wrong here. There's one possible issue.
No.
Yeah, I mean, I have a sequence. I might as well start the sequence at 1. I'm not a computer scientist starting at 0. There's one thing that might go wrong.
A sub n can't be 0?
A sub n can't be 0. So if one of the ANs happens to be 0, we're in trouble. So what you would have to do is, this is assuming no ANs are 0. If some are 0, just multiply by z to the r for some r. And you can easily fix what's going on at the origin. I can't have z divided by 0. So I might have to just put in some number of copies of z if some terms in my sequence are 0. So if 0 occurs 5 times, it's in my list 5 times. So now I have a product like this. This is extremely wasteful. What I'm doing is the deeper down I go, the larger my n is, and so the more terms I'm taking in my expansion. In general, this is what's known as enormous overkill. How many of you have heard expressions about atomic bombs?
Question.
Yes?
Actually, why is this multiplying by z to the r, remove the zeros, and what would the r be?
Well, no, I'm just saying r is going to be the number of zeros at the origin. If I give you a list with prescribed zeros,
Yeah.
I can't have an be 0 in this expression over here.
Sure.
So I would have to start maybe at r plus 1. So start product at r plus 1.
So you're saying that if we have zeros, just find all of them. And
Just
start
find, it's the zeros at 0. The zeros at 0 are the problems. Because I can't divide by 0. If an is 0, this makes no sense.
Okay.
So one of you have ever heard like an expression, swatting, a gnat with an elephant gun or an atomic bomb? If you want to kill a little fly, one way to do this is to drop an atomic bomb with several kiloton megaton yield on the fly. That will kill the fly. What's wrong with this?
Kill everybody else.
Yeah, there's a lot of collateral damage, right? You are using far more than you need for that itty-bitty fly. If you're Mr. Miyagi, you can just do it with, oh no, Mr. Miyagi couldn't do it. It was Danielson. You ever seen Karate Kid? Right? Danielson is able to kill the fly with just 2 chopsticks. Okay? Now, what's the advantage of using the atomic bomb? You know you got the fly. The fly is dead. Right? That's kind of satisfying if your goal is to kill the fly. If your goal is to kill the fly with the least possible damage, with the least possible disturbance, this is enormous overkill. This is enormous overkill. This is equivalent to dropping an atomic bomb on your set of zeros. It's going to converge. But the way it converges is I am potentially putting in so much extra decay with these exponential factors that my expression is far more complicated than it needs to be. At the end of the day, I want to have a nice function I can work with. This will converge, and now I'm going to have a product. How do I show my product converges? I do exactly what I did before. Each term is going to look like e to the negative 2 over zn. So we have a few minutes left. I'm going to try to leave this on the bottom so we can keep this up and just look and see what our product is going to look like. So I'm going to assume in just what happens below that we don't have any zeros at the origin and that everything is good. So assume never 0 at 0 and all the ANs are less than or equal to 1/2. Otherwise, you just have to deal with those few exceptions by themselves. So we have the product n goes from 1 to infinity of En of z over An. This is the same as the product n goes from 1 to infinity. Well, here, it's less than or equal to, I'll put in absolute values. E to the negative 2 z to the n plus 1. I'm sorry, z over An to the n plus 1. That's from the estimation we just did earlier, right? Each of these En of z over An, as long as z over An is at most 1/2, I'm sorry. So I want all z over An less than or equal to 1. So what does it mean for z over An to be less than 1/2? Well, my sequence An is going off to infinity. I take some ball and say z lives inside a circle of radius r. Eventually, since the ANs are going off to infinity, eventually z over An is going to be at most 1/2. Right? Because z, if it lives inside a ball of radius r about the origin, eventually z over An will be at most 1/2 an absolute value. So that means the En of z over An is going to be at most this. And now, if you want, we can write this in terms of what we've done before. The exponential is 1 minus 2 z over An to the n plus 1 plus really small. And I take a product and goes from 1 to infinity. This sum converges. It's a geometric series. I've got all those other terms here. You can just incorporate those, change the 2 to like a 1. You can handle all that stuff with just a little bookkeeping. And so I urge you to read the book and see the bookkeeping. This is going to be squares of this. It's going to be much lower. This is 1/2 to the n plus 1. The next term is going to be like 1/2 to the 2n plus 2. Very small. So now, because of what we know about series and products, this sum converges. Therefore, the product converges. And so since the product converges, we've found a function. But we've potentially found a function that's far more complicated than needed. So on Monday's class, which is really going to be on Wednesday, I'll talk just a little bit more about the overkill, and then I'll email you what we're going to be looking at next. So again, you're welcome to start the exam whenever you want. The exam is due